Assalamualaikum warahmatullahi wabarakatuh. My name is Afza Alina Fana bin Jamuddin. We are from group 420 and we wanted to present about chapter 18 and chapter 20. First, we need to focus on chapter 18, which covers about the temperature. What is actually a temperature? Temperature is a properties that determines whether an object in thermal equilibrium with other object. For the next slide, we will see about the difference between the thermal contact or thermal equilibrium. Thermal contact. Energy can be exchanged between object by heat or electromagnetic radiation due to the temperature difference. In thermal contact, we have the term energy can be exchanged due to the temperature difference. While in thermal equilibrium, two objects will not exchange the energy by heat or electromagnetic radiation because they are in the same temperature. Next, we will look at the zeroth law of thermodynamics. And zeroth law is also called as the law of equilibrium. What is the law of equilibrium? If object A and B are separately in thermal equilibrium with the third object C, object A and B are in thermal equilibrium. What is the thermal equilibrium? Energy would not be exchanged due to the same temperature. Next, we will look at the physical properties that may change the temperature. First, volume of the liquid. Second, dimension of a solid. Third, pressure gas at a constant volume. Next, volume of gas at a constant pressure. Next, electric resistance of a conductor. And the last one is color of an object. In this topic, there are also terms that we need to focus on. The first term is the ice point of water. The word ice point is referred to the 0 degree Celsius compared to the steam point of water. Steam point of water refer to the 100 degree Celsius.
Next is thermal expansion of solids and liquids. Okay, first, thermal expansion is a consequence of the change in the average separation between the atoms and object. So we have three thermal expansion, 1D for length, or it is also called as linear expansion. Second one is 2D for area and 3D for volume. Okay, so for 1D, we use equation delta L equals to alpha at initial delta T, where alpha is the average coefficient of linear expansion. And then for 2D, the equation is delta A, because 2D is for area, so delta A equals to gamma A initial delta T, where gamma is to alpha. And then 3D is equation delta V equals to beta V initial delta T, where beta is equals to 3 alpha. Okay, next is macroscopic description of an ideal gas law. We use ideal gas model to make predictions that are adequate to describe the behavior of real gases at low pressure. So 1 mole of any substance is the amount of the substance that contains Avogadro's number in a particles, which Avogadro's number is equals to 6.022 times 10 to the power of 23. So number of moles, N is equals to mass over molar mass of the substance, and there are three observations. So the first one is gas kept at a constant temperature, pressure inversely proportional to the volume. This is described as Boyle's law. And then the second one is Charles' law, where pressure of gas is kept at constant, so the volume is directly proportional to the temperature. And the last one is Gay-Lussac's law, where volume of the gas is constant, and pressure is directly proportional to the temperature. So these three observations are summarized by the equation of state for an ideal gas, PV equals to nRT, where R is the universal gas constant, 8.314 joule per mole Kelvin. And we also have another one equation, PV equals to NKBT, where KB is the Boltzmann constant, equals to 1.38 times 10 to the power of 23 joule per Kelvin. So before we end, let's look at a question. So question 17. So the question asks for option, and they give us T initial negative 10 degrees Celsius and Young modulus 20 exponent 10 Newton per meter squared. So first we use equation delta L is equals to alpha L initial delta T, where this is the linear expansion. And then the second one, Young modulus equals to F over E over delta L over L initial. So we use these two equations and compare these two. So we get delta L equals to FL initial over Young times area, and also equals to alpha L initial delta T. So the question asks for tension of the wire, which is F. F equals to Young modulus times area times alpha delta T. So we just substitute the data here, and then we get the answer 396 Newton. This is answer for A, tension of the in the wire. And then B, the question asks for T initial. So give us stress of the steel 3 exponent 8. So we use equation stress over Young times alpha here equals to delta T. So we get delta T equals to 136 degrees Celsius. But this is not the final answer. The question asks for initial temperature. So T initial equals to T final minus delta T. So we get negative 101 degrees Celsius. So this is the final answer for B. And then C. So the answer is no changes, because from part B, we compare equation for delta L and Young modulus. So we already divide L. We already remove the L initial. So L does not line does not affect any calculation here. So that's why there's no changes, even if the Golden Gate Bridge were twice as long.
For the Islamic value, we choose patience because we know that in physics there are so many calculations to get the final answer, and sometimes we may get error in order to get the final answer. Okay, so what is actually a patience? Patience is actually holding tongue from complaining and body parts from harming himself or others. So Allah has mentioned about patience so many times in Al-Quran and As-Sunnah. For example, Allah has mentioned about patience in Surah Az-Zumar. Allah said that only those who are patient shall receive the rewards in full without hisab, without limit, calculation and estimation. So from the Holy Ayah Al-Quran, we can conclude that no matter what is the situation that we are facing right now, we need to be patient, and we need to believe that Allah is always with us and He never leave us alone.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And my name is Adam bin Muhammad Azharuddin. Metric number is 2200 and 77. So today I will explain to all of you about chapter 20 in physics 2, the kinetic of theory of gases. Okay. Number 1, molecular model of an ideal gas, and number 2, molar specific heat of an ideal gas. So let's begin. Number 1. So molecular model of an ideal gas, we can see that kinetic theory assumption that first physical component have 3 points that myself has read it, that the gas consists of identical molecule within a cubic of side length, which is D. The number of molecule in the gas is large, and the average separation between them is large compared with their dimensions. And the molecule occupy a negligible volume in the container, which is from here we can see that the volume that negligible in their own container. So for the second one, behavior of the component. The molecule obey Newton's law of motion, but as a whole, their motion is isotropic, which I know that all of you guys are already studied, already learned it in our class. The molecule interact only by short range during elastic collisions. Because of their short range, they are collision only by during elastic. And for the last one, the molecule make elastic collision with the walls of container. Moving on the equation, we can see here that K total transfer equal to N times by 1 over 2 mv square equal to 3 over 2 N Boltzmann constant T N equal to 3 over 2 nRT. They are all related and we can use all of them in to do the equation. For the next part, we move on to the next part. We can define a specific heat for two special processes that we have studied in chapter 19, which is isovolumetric and isobaric, because the number of mole and convenient measure of the amount of gas. We define the molar specific heat associated with this process as follows, which is Qn constant value delta T and Q equal to N constant pressure delta T, where Cv is the molar specific heat at a constant volume and Cp is the molar specific heat at constant pressure. At constant volume, no work done on the gas. The only change in the system is the change of internal energy. Do you know what I mean? The things that change only the internal energy. Therefore, the heat Q equation of the constant volume has the same equation as the D internal because of the Q delta E isovolumetric and isobaric. Let's move on. We can express the molar specific heat at constant volume as constant volume equal to 1 over N times delta E internal over delta E. We see that the internal energy E internal of N molecule or N mole of an ideal monoatomic gas is E internal equal to K total translate. We just show right now, which is this one. Hope you guys see it. Last part for our chapter 20, P is the constant pressure at which the process occurs. Applying the first law of thermodynamics to this process, we have delta E internal equal to Q plus W, which is equal to N constant pressure delta T plus negative P delta V. Because PV equal to nRT, note that for a constant pressure process, which is P delta V equal to nR delta T. Substituting this value for P delta V into equation above with delta E internal equal to N constant volume delta T. Give this one over here. And the final result will be constant pressure minus constant volume. We will get the R. So this expression applied to any ideal gas. It predicts that the molar specific heat of an ideal gas at constant pressure is greater than the molar specific heat at the constant volume by amount R. The universal gas constant because constant value equal to 3 over 2 R for a monatomic ideal gas. We can predict that constant pressure equal to 5 over 2 R equal to 20.8 joule per mole time over K, time K. For the molar specific heat at the constant pressure, the ratio of the molar specific heat is a dimension quantity. Gamma Greek is gamma equal to constant pressure over constant volume, or we can say that if 5R over 2 over 3R over 2. And we can get 5 over 3 and the final answer will be 1.67. And that's all from me.
Subtopic 20.3, the equipartition of energy. The subtopic we relate the energy that is associated with the motion of the molecule. Okay, let's consider an atomic gas. This molecule have the shape of the dumbbell, like this diagram, where they are the center of mass of the molecule that can be translated by X, Y, and Z direction. The grey arrow show the direction where the rotation is only happen in the X and Z axis, where the Y axis can be neglected because the molecule's moment of inertia and Y and its rotation energy. But this axis are negligible compared with those associated with the X and Z axis. So there are 5 degrees of freedom for translational and rotation. There is 3 associated with the translational motion, and the 2 associated with the rotational motion. So each degree of freedom contribute the average energy per molecule and the internal energy per system of a molecule. And in the vibration, for now that we can find the E internal with this equation, and from the equation we can use this to find the molar specific heat at a constant volume, and we can predict the molar specific heat for the constant pressure, and we eventually find the ratio of molecular specific heat for the atomic molecules. Okay, moving for the subtopic 20.4. So we already know the adiabatic gas, and the heat transfer is 0, so the E internal is equal to work done on the gas. So the internal energy of an gas depend on the temperature. The change in internal energy in adiabatic process is the same as the isovolumetric process between the same temperature. That is question. So in this diagram, we can found that the T initial to the T final is decrease the temperature in an adiabatic expansion. By the definition, there is no heat transfer, and we can see that the graph is from the graph the temperature is decreased, so the delta E internal is also be negative. And during this expansion, we can equate the equation with this. We can to differentiate the initial and final properties, and we can also use this equation if we only have information about the temperature and volume. Yes. Okay, that's all from me. So before we end the presentation, should be grateful that all of this that we learned so far has benefit us. So we should be grateful to Allah Subhanahu Wa Taala. All of this is benefit for all of beneficial to all. Thank you.